Welcome to Let's Get to the Marks. We're looking at Kc, so let's get into it. Question 2. Tetrafluoroethene is made from chlorodifluoromethane in this reversible reaction. So we have 2 moles of chlorodifluoromethane, reversible symbol, and then we have 1 mole of tetrafluoroethene plus 2 moles of hydrochloric acid or hydrogen chloride. And the enthalpy change is plus 128 kilojoule per mole to the minus 1, so that's endothermic. A 2 mole sample of CHClF2, that's the chlorodifluoromethane, is placed in a container with a volume of 23.2 decimeters and it's heated. When the equilibrium is reached, the mixture contains 0.270 moles of chlorodifluoromethane. That was the initial reactant. Okay, calculate the amount in moles of C2F4 and HCl in the final equilibrium mixture. Okay, I am going to rewrite out the equation, but I'm going to simplify it without the state symbols or the reversible symbol, just because I just want this for the purposes of this equation. This is going to help me with this calculation, basically. So I'm going to write this out. Now I'm going to make a little table some of you may have been familiar with. Different people write different things on the side of the table. So people do this when working out the amount of moles in an equilibrium mixture. They make a little grid like that of the products and reactants, and then I write I. So it tells us, which I've highlighted up the top, that we've got 2 moles of CHClF2, and we can't have any moles of the products yet. So no moles of C2F4 and 2HCl. So how much does it change by? Well, if you take the 2 moles that we have of the initial reactant, and then it tells us how much of the reactant is left afterwards, which is 0.270 moles. So let's do 2 minus 0.270, and that is going to give us the amount that those moles changed by. And the answer, of course, is going to be 0.173 moles. So what happened is, of our 2 moles of initial reactant, 1.73, moles were used up, leaving behind 0.270 moles. Now, as the ratio of our reactant to our first product is 2 to 1, it means we only get half the amount of moles used up or created, of the product. So we go 1.73 divided by 2, because the ratio is 2 to 1, and we get 0.865. So at equilibrium, we have 0.865 moles of the first product. Now we look at the relationship between the reactant and the final product, the second product, the HCl. We find that it's 1 to 1. So as we used up 1.73 moles of the reactant, it means we produced 1.73 moles of the product, the HCl. So the amount of tetrafluoroethene is 0.865 moles, and the amount of hydrogen chloride is 1.73 moles. Okay, let's move on to 2.2. So what do we have here? Well, I'm reusing the equation here, and it says give an expression for Kc for this equilibrium. Excuse the fact I don't have state symbols or a reversible symbol in my equation. So when you're writing out Kc, you just need to think products over reactants. So let's write down the products. Now we need to put them in brackets, square brackets, because that stands for concentration. So those square brackets mean mole per dm to the minus 3, so it saves you having to write that out. Now I put a little 2 outside the HCl. Why do I do that? That is because there are 2 moles of it, so it's to the power of 2. And for the bottom, the product, CHClF, we put a little 2 outside as well, and that's your equilibrium expression for Kc. Okay guys, don't forget to pause the video and have a go at these. So 2.3, calculate a value for Kc. So what we need to do here is just simply plug the units in. So 0.865, that was the moles of C2F4. And if we look back at the original stem of the question, or are working out to the first part, 1.73 were the moles we worked out for HCl. And the moles of our reactant at equilibrium was 0.270. Now I'm putting the little sign for the power of 2 outside because there were 2 moles of it. Now, something that we've also got to take into account is that in the stem of the question, it told us that we had 23.2 decimeters. And it's said right here in the stem of the question that these were placed in a container with a volume of 23.2 decimeters. So we need to make sure that we divide the moles by the decimeters to get the concentration, and then we square the results for the ones we need to square. And if you do that, you're going to get the answer of 1.53, but now you need to work out the relevant units. And as you can see, there are mole to the dm to the minus 3, mole to the dm to the minus 3 on the. And this is because I have 1.73 to the 2. So there's 2 mole to the dm minus 3s. And just with below, I have 0.270 to the 2. So I have 2 mole to the dm minus 3 there, which makes my units, because those all cancel out, mole to the dm minus 3. And so there's our answer, 1.53 mole per decimeter. 2 marks, or 3 marks, with the working out. Okay, for 2.4, state and explain the effect of using a higher temperature on the equilibrium yield of tetrafluoroethene. I suggest you pause the video, have a go. Okay, I'm writing out the equation here again with the reversible symbol and the gaseous symbols. We actually don't need the gaseous symbols for this because we're not talking about pressure, which is where you look at how many moles of gas are formed on each side of the reversible symbol. We're actually more interested in the delta H, the enthalpy of this reaction. And it's plus 128 kilojoule per mole. And that tells us it's an endothermic reaction. So what's the effect on yield if you increase the temperature? Well, if you increase the temperature, the yield's going to increase. But why? That's because the forward reaction is endothermic. You see the plus 128? So the forward reaction is endothermic. Remember, if you increase the temperature, our reaction, the equilibrium will shift to oppose the change you've made. Remember, that's Le Chatelier's principle. And that means the equilibrium will try and oppose the change. And so to oppose your change of increasing the temperature, it forces it to the side that takes in energy, the endothermic side, which is the right-hand side. And that's why the equilibrium shifts in the forward direction and we get a higher yield. So your 3 marks here are 1 for stating the effect on yield, which is that it will increase, 1 for saying the equilibrium will shift to oppose the change, and finally that it shifts, therefore, in the forward direction. Chemists provided evidence that was used to support a ban on the use of chlorodiafluoromethane as a refrigerant. Many refrigerators now use pentane as a refrigerant. State the environmental problem that chlorodiafluoromethane can cause. Give one reason why pentane does not cause this problem. Well, that's a CFC, and so we know it destroys the ozone layer and breaks down or contributes to the depletion of ozone in the ozone layer, thinning it or making holes in the ozone layer, which is pretty dangerous because it lets ultraviolet radiation, the dangerous ultraviolet radiation, through. So why does pentane, as I'm drawing out here again but a second time, why does this not cause the problem? And it's to do with a particular bond that you don't find in pentane. So what makes chlorodiafluoromethane dangerous is the CCl bond, and of course pentane doesn't have a CCl bond. So it doesn't form free radicals that break down the ozone layer. And that's your answer. There we go. Hope you liked it. Remember to share, subscribe, like, and let's get to the marks.
You're still here? It's over.